So Heather Reeves is a research scientist at National Severe Storms Laboratory in Norman, Oklahoma. She got her undergrad degree at Central Michigan, Fire Up Chips, and then went to North Carolina State for her MS and PhD. Strong interest in orographic meteorology and winter weather. And we were just talking here earlier. It's like I can't think of anybody who's doing more with respect to precipitation type research in the United States than Heather. But today, she has a real exciting project that she's working on with Shawn at OU on the development of probabilistic subfreezing road surface temperatures using MRMS and the HRRR. A really exciting project that I think has a lot of potential for operational use. One thing that I really like about Heather is a lot of her research is very, very operationally oriented. And this is something that could really pay dividends for us in the Weather Service as far as our impact decision support services. So with that, Heather, I will turn it over to you, and maybe you can introduce Shawn to the crew.
That's great. Thanks, Randy, and thanks for that very nice introduction. I have to give a lot of credit for this idea to you because it was at a different webinar series where you first started talking about this issue of road weather that got me interested in the whole topic to begin with. So really, right back at you. But Shawn Handler is a research associate who works with me here at NSSL. He has a master's degree from the University of Oklahoma. He's done quite a bit of research with radar meteorology and did his master's degree in convective springtime weather, but had such high recommendations from people. I needed somebody, and he was ready at just the right time, and I gave him this job, and he came up with some techniques of extracting the road temperature from data that I wouldn't have thought to do. And I had a lot of doubts when he said he wanted to do it this way, but he's proven me wrong, and I'm now a convert, and I hope that you'll be a convert at the end of this talk too. So Shawn, I'll let you take it away.
Thank you, Heather. Okay, so we'll get right into it. I'll be talking about our road temperature Nowcast model, which we use some machine learning for. And so the overall, motivation for this is, on average, 6,000 people lose their lives due to adverse weather conditions on the roads. And roughly 20% of that is due to wintry precipitation. And so obviously, if we want to know whether or not snow or ice is accumulating on the roadway, we need to know if the road temperature is subfreezing or not. And so that's what this work is going to show. And this work lays sort of the foundation for a future transportation hazards product suite in MRMS, in which this road temperature model would be used for that. And so the figure on the right is a prototype image for one of those future products, maybe, that would show you what the current road conditions are. And so maybe in some regions you have accumulating snow or ice, or maybe the roads are just wet. But this road model would be used sort of as inputs into creating that. And so, return.
Oh, you got to click
forward.
on it.
I have to click on the screen. Spacebar. Okay, there we go. All right, technical difficulty. So a little bit of background. We're not the first people to ever look into this. The most widely known model is METRO, or Model of the Environment of Temperature and Roads. It was developed by Canadian Meteorology Agency, and it's being used experimentally within the NWS now. But it's a physics-based model that solves a lot of the near-surface energy balance, a lot of those flux equations, and it uses both surface observations from the ARWA sites, along with NWP output to produce up to a 48-hour road temperature and hazards forecast. Like I said, it's been used experimentally in the NWS for the last decade, and it's shown a lot of skill in regions of complex terrain. So the METRO model performs well, but we saw some limitations for what we want to do within MRMS. And these limitations aren't necessarily limitations for the METRO model, but just why we thought the METRO model wouldn't be appropriate for what we want to do. The big thing is that METRO provides a point forecast. And so you can only have this road temperature and hazards forecast wherever you have the surface observations, which require the ARWA site. And as it turns out, the ARWA sites are not in every state. I'll show in 2 slides sort of the spatial distribution of the RWIS sites across the CONUS. And you'll see that some states don't have RWIS sites, and some only have RWIS sites along major interstates or highways. There's also a couple other questions. One question is, how would you accurately assign a temperature in between two RWIS sites? So the RWIS sites might be spaced, every certain number of kilometers, and how would you sort of accurately assign a temperature in between those locations? That's one question. And then the last is there's actually a little bit of uncertainty with the RWIS temperature observations themselves. And would it even be appropriate to have a deterministic forecast for this? So to go into a little bit more detail with that, the figure on the left shows a traditional RWIS sighting. So you can imagine the actual RWIS unit would be just off to the right of the screen, but each one of those black boxes represents those temperature sensors, and they're installed flush with the surface of the road. And they're installed along the wheel track, or inner wheel track, and you can see that there's roughly one per lane. But for each one of these temperature sensors, they can each report a different reading. And these differences can be small sometimes, but they can also be large. And we've even seen instances where those differences are up to 5 degrees Celsius. And so we can speculate as to some reasons why this might be happening. The first is traffic. Maybe one lane is traveled more heavily than others. Maybe there's a difference in road conditions. Maybe one side of the highway is newer than the other. There can be some shading effects from nearby vegetation, but also when they place these RWIS sites, sometimes they'll place them near overpasses, and they might have one sensor that's on an overpass, and they might have the rest that are on the main roadway that's flush with the ground. And so you can have differences there. There can also be improper installation of these sensors themselves, which can result in roughly 1 degree C error, not as large as the other reasons, but still error nonetheless. And so kind of with this uncertainty and some of those limitations I mentioned on the previous slide, we wanted to steer away from the deterministic forecast that Metro would provide, and instead opt for a more probabilistic approach. And so our final product is a 1-hour probabilistic Nowcast, in which we estimate the likelihood that a road temperature is at or below freezing. And so to do this, we use some machine learning, specifically a random forest, which is a collection of decision trees. I won't go too deep into that, but we feed it in various input data, primarily her model data, but also some MRMS radar variables and MRMS derivatives. And we match all of that with the RWIS road temperature observations. And so the figure on the right shows all those RWIS sites across the CONUS. And as you can see, some of the states, or primarily all the southern states, with the exception of Georgia, do not have any RWIS sites. But some states like Colorado and Missouri, they really have a lot of their sensors close to the metropolitan areas or along major interstate highways. But for our purposes, we chose 675 sites, or basically all the sites, or all the locations with a red dot on that figure. And that's a diverse enough sample where we got some observations from the Central Plains, some in the eastern half of the CONUS, but also in regions of complex terrain. And we chose the coldest temperature observation from the RWIS site if there were more than one observations, because we just want to focus on whether or not the road is actually subfreezing or not. So a little bit more on the methods behind this. We had 2 years worth, or 2 winter seasons worth of data to play with. And for us, we defined a winter season from October 1st to March 31st. So we had this past winter and then the 2016-2017 winter. We used the 2016 and 2017 season for training, and then the second season for testing and probability calibration. And from the 2017-2018 season split, we have 8 weeks worth of true testing that will be used to report our statistics on. And so basically what we did overall is whenever we had a HRRR model run, so each hour, we would extract all of the relevant features that are used to train the model. We'd extract those at the nearest grid point to where that RWIS is located. Or technically, the box wherever the RWIS location falls within. And so we do this for each hour, for each day during that 6-month period, for all of those for all those RWIS locations that had a red dot. We actually get a lot of training examples. We had roughly 5.3 million 1-hour examples after we took QC into account. So we have a lot of training and testing data to play with. And so we'll start getting into it. We'll look at 2 case studies first. The first one is a fatal car pileup on I-44 in Missouri this past February. The top panel shows sort of like a METAR for one of the nearby ASOS stations. So the blue line is the 2-meter temperature time series, and then the little plus marks in the top right represent when the ASOS was reporting snow. The bottom left figure is our actual output from our algorithm. So color-filled is the probabilities of a subfreezing road, valid at the time of the accident, which was at 23 UTC. Also shown on that in that figure are the RWIS sites themselves in Missouri. Those are the black circles. If the circle is filled, then the RWIS was reporting a subfreezing temperature at that time. If they were open, then it's above freezing. So you just primarily along both major interstates. In Missouri, the RWIS sites were reporting subfreezing road temperatures, and the red open circle is where the accident occurred, roughly. And then the bottom right panel is a comparison of our product, which is the red time series, our forecasted probabilities, compared to the nearest RWIS site to that accident and its observations, which is the blue time series. And so for this event, temperatures were decreasing throughout the day. It wasn't until roughly 17 UTC that the air temperatures themselves were beginning to fall below freezing. And it's pretty close to that time when snow began falling. Our probabilities were virtually greater than 85 to 90% throughout much of the I-44 corridor at 23 UTC when this accident occurred. And looking at just at the RWIS site closest to the accident, the 2 time series are they're pretty much 1-to-1. We had really high probabilities when the event occurred, and so our model performed very well here. The second case study is in regards to an unusual snowstorm in Mississippi this past December. We chose this case because, for one, it was an unusual snow event in the southeastern U.S., but also because the winter storm severity index was pretty high for this event. So they were expecting some impacts to travel. But as it turned out, those impacts actually weren't as bad as anticipated. And so the figure layout is very similar to the previous slide. The only major difference here is that we don't really have any true verification because Mississippi does not have those RWIS sites. And so we have to go based off of media reports and the post-event discussion by the Jackson forecast office. And so for this event, air temperatures weren't as cold as that Missouri case. They were the air temperatures themselves were pretty close to freezing, especially when it was snowing. And our probabilities from our model never crested above 40%. I think the max was right around 35, which occurred during the heaviest snowfall period. And as it turned out, from the post-event discussion from the Jackson forecast office, they said that that snow was really only accumulating on elevated surfaces, grass and trees, kind of like what this figure shows, or this picture shows. But the roadways themselves really, they weren't impacted as much as anticipated. There was some slushy accumulation, but roads were not completely impassable. And so with our probabilities on the low end, they're not completely zero, but they're not extremely high. We think that our algorithm performed well for this event as well. Now we'll go into more of sort of like the statistical analysis piece. On the left is the ROC curve, and each line corresponds to one of those 8 testing weeks, and the more bold blue line is just the mean curve, the mean of all those curves. And we would like to see all the curves up near the top left of the figure, which we do. The area under those the area under the mean curve is roughly 0.97, which is a really good metric. And then on the right, we have the performance diagram. Again, each curve is for one of those testing weeks. And here we would like to see a lot of the curves up near the top right corner, where you have the higher values of the success index. And we see that there's a little bit more spread. Some of the weeks perform more optimal, or we see more optimal performance from the algorithm in some weeks compared to others. Most noticeably is the light blue or cyan blue curve, which represents the week of October. The performance for that week was not as optimal as we would like. We have a few hypotheses for that. The first being in the month of October, we really didn't have that many training examples of subfreezing road temperatures, and these machine learning models can struggle to find these patterns if you have a lot more of one class compared to another. So since we had a lot more of above freezing road temperature observations, the model's having a little bit of a struggle to learn some of those patterns. Or it could have just been that the synoptic pattern for that week maybe was just different than something that it saw in training. Could be a combination of both of those two factors. Next, on the left, we have the reliability curve. And here we would like to see each of those curves following the perfect reliability curve, which goes from the origin to the 1-1 coordinate, or the 1-to-1 slope line, if you want to think of it that way, which all of our curves do. If they fall, or if they lie within the shaded region, the algorithm is said to have skill with respect to climatology. And if you're looking for a metric that just kind of gives you the answer straight away, you could look at the Breyer skill score. And the Breyer skill score is 0.71. Anything greater than 0 is deemed to have skill, which we have. And so that's really encouraging. And then on the right, we have the output probability distribution from our algorithm, as represented as the little histogram. And here we'd like to see a lot of counts near 0 and near 1. That means our model is considered sharp, which it is. We see more counts centered near 0 and 1 compared to in the middle range. But we also overlaid on that distribution some meteorological variables, more specifically the variables that are used as input features in our model. And so the top two show the 2-meter temperature on the left and the surface temperature on the right. The solid blue line is the mean, and then the 2 dashed lines represent the 10th and 90th percentile values within each bin. And so you can see that whenever the air temperature, surface temperature are pretty much well below freezing, there's a really high chance that the model is going to say the road temperatures are subfreezing. Conversely, if you're above 0 degrees, then the model is going to say the probabilities are pretty low. But if you're in that middle range, you're between, we'll say 0 to -5 degrees Celsius, you're kind of in that range where the the output probabilities may be indicating a subfreezing road, or it may not be, which is just the nature. And then the bottom two figures show similar. Sorry, the bottom two show the number of hours that the 2-meter temperature and the surface temperature are below freezing. So we kept a running tally on that. And you can see here that if we've been below freezing for a day, then more likely than not, the algorithm is going to say that the road temperatures are sub-freezing. But if it's only been a few hours, it may or it may not. There's a lot of spread there. It would probably depend more so on how many hours we've actually been below freezing. But it's just good to show that how meteorology would tie into the model, making the predictions that it is. We can also look too at the most important features that the random forest identifies. And not too surprisingly, a lot of our surface-based features are considered most important. The upward long wave radiation flux was the second most important. And then we had a few derived variables down below, which were not as important, but were still considered within the top 10 of important features. And all of the results that I've been showing up to this point were for our 1-hour Nowcast, but we've also been experimenting and transitioning more to the forecasting side, in which we look out to longer lead times to see at what forecast hour would this model lose skill. And to do that, we had to look. We can keep looking at the HRRR. We can go out to 18 hours. But we also started looking at the GFS and the NAM. Excuse me. And so here we're showing those reliability diagrams for those different models and their forecast times. So for the GFS, for the 36-hour forecast, that's panel A. Panel B is the NAM 36-hour forecast. And panel C is the 18-hour HRRR forecast. And the HRRR forecast looks pretty identical to what we saw compared to the Nowcast, which is encouraging. But we even see still quite a bit of skill in all three models regardless. The GFS and the NAM, their reliability curves look a little more rough, I guess, not as smooth compared to the HRRRs, and that's probably because of the fact that since those models aren't run as frequently as the HRRR, we don't have as many training and testing examples to use. But regardless, looking out at least to 36 hours, as of right now, our model still has skill better than climatological forecasts. And we are anticipating looking out even further, maybe to 48 hours and beyond, to see, to exactly what point would these forecasts lose a lot of skill. And so one other thing we're doing, which we've already done, is to get the Nowcast product up and running on the MRMS experimental website. And so we can do that now. I can show you guys. Oh, wow, that was easy enough. Drag it over. Maybe. I probably have to exit this. There we go. Trying to get a panel on the screen to show you guys. There we go. Okay. All right. How do we zoom in? Okay. Just gotta zoom. Is there a way we can zoom in on the screen? Okay, well, anyway, I'm going to try and zoom in a little bit more because the screen looks a little small. But what we're showing here are those probabilities. So the probability that the road is sub-freezing. And this is what you could see on the website, obviously. And you can go back in time if you really wanted to look at this past earlier this week, the past snowstorm that we had. But the probabilities are color contoured. And this, we should say that these probabilities are going to be assigned everywhere regardless, whether there's precipitation falling or not. And these probabilities are a 1 hour forecast. So right up here in the top, we're at 16Z. This is when this data was generated, but it's valid for 17 UTC. So in case anyone ever wants to look at it, just remember that the probabilities are valid for the next hour. Okay. So for future work, in addition to implementing this on the experimental website, the main thing we're going to be doing is testing how far out into the future we can provide a forecast before it loses skill. We also will be obtaining some end user feedback, forecaster feedback, when this product's evaluated during the upcoming winter weather test bed hosted by the WPC. We're also going to be trying to improve the model using both this upcoming season's worth of data, winter data, and we might even see if we can add some other features that maybe would help explain or improve the model during some events that it doesn't perform as optimally. So, and we'll also be looking at tinkering with different thresholds for what's considered freezing, because for some events, the state DOTs will lay down different chemical solutions based on what the anticipated temperature will be. And those solutions basically lower the freezing point of water, so it might be useful to look at some lower thresholds below 0 degrees Celsius. So, but with that, we're done. And if anyone has any questions, we'll take them or comments.
Hey, thanks, Shawn. Appreciate it. Great presentation. Got the window open. Anybody has questions, feel free to raise your hand and we'll unmute you. While we're waiting, Shawn, I had one. I was kind of curious. Well, and just for everybody, all the Sues on the call, this is something that we're hoping to get into AWIPS if possible this winter for you all to look at. In the meantime, that website that Shawn showed, you can look at it right now. One question I had for you guys is what about the verification, kind of in the sweet spot? You showed like hours that it's been below freezing and that sort of thing, and kind of the skill that you see there. What about in that transition zone when the temperature is really changing or falling along cold frontal passages and you're going from road temps in the, say, mid to upper 30s and they're falling into the upper 20s? What's the skill look like in that? And have you done any specific verification based upon like based on the change of the road temperature when you compare it to the RWISs?
We have not looked at that specifically yet. That's actually on our to-do list. We were talking about that last week because we want to see, for these quick changing events, how well does our model perform. So I don't have any true verification statistic on that right now, but it's a work in progress as well.
Okay, thanks for that. Looks like we have a question. Tom Holtquist, you are unmuted. Oh, wait. He says he doesn't have audio capabilities. So the question is, he's curious why we cannot get to that website that you shared. I've been on that website.
If you can't reach the web page, please email to me what your office's IP address is. It is only accessible from .gov IP addresses. And we've tried to open up as many that we know of that exist in the National Weather Service, but I know, so all the regionals are open, but if you're for some reason not routing through your regional, but you're doing it a different way, we may not have gotten you. So if you get with your IT people and have them tell you what your external facing IP address is and email that to me, I can have your address added to the list of cleared sites.
Okay, thanks, Heather. Another question was, would this presentation be available for the staff? And TJ, yes. Pat Spoden actually chatted me the same thing. What I'll do is I'll make a clean copy of just the presentation without all the rest of the pseudo call around it, and then share that with everybody so you can forward this to your staff. Tom, TJ indicated that maybe you need to include the HTTPS if you didn't have that on the front.
Yeah, that's true. That needs to be there. Yeah, if it's just HTTP:// it won't work. There has to be that S in there.
Yeah, that looks like maybe what it was. Any other questions? I'm not seeing any. Oh, wait, here's one from Ed Ray in Jackson. He's curious if there are plans to incorporate snowfall intensities, thinking along the lines of snow squalls.
That would be an extension of this product. So we would use this model, the probability of the subfreezing road, and we'd probably use this output with probably some radar, some radar imagery, all the different radar variables, and have a new product that would show whether or not maybe there would be accumulating snow on the roadway or freezing rain if it's raining, such like that.
Yeah, that's part of the long-range goal. In fact, that was what I envisioned as the end product to begin with, is just the hazards themselves, like accumulating snow, accumulating ice, water on the roads, that sort of thing. But as Shawn started to round the final corner of the initial development of this road temperature model, it occurred to me this in and of itself has some utility. And wouldn't it be useful if we could get feedback on this by itself now, because we don't sit there and look at the weather day in and day out like you guys do. And we get together once a week and do a stand-up where we Google news stories on car accidents due to snow, and we'll watch the media videos, that sort of thing, and scrutinize those and say, well, I can see that this accident happened on an overpass. Let's zoom in and see what our thing did. But that day in and day out experience, we can't devote our time to just day in and day out looking at the weather. We have a different kind of a job, but you guys, that is your job. And so we thought, what if we get this out here in front of the forecasters early on, and we plan on putting out like a Survey Monkey kind of thing in the next month or so, where if you see something that doesn't look right, the see something, say something, that's what we want. We love hearing about the successes, but if you see an event where it didn't seem to work well, or you had difficulty interpreting it because of some reason, that's incredibly beneficial to us as we go forward and we develop this product and then the follow-on products that go with it.
Okay, thanks, Heather. We had a question here in the room.
Yeah, this is Andy. Thanks again, Heather, for this. And I'm gonna try and get this into AWIPS. So just need to look at how we can get the data. But once we get it, the concept would be I'll add it to the dam, add it to the National SmartNet, and add it into Forecast Builder so we can use it to populate the road, populate the road temperature grid that we already have there. Because as you know, it'll just help give you that additional freeze and rain introduction in some of those scenarios when you're dealing with liquid at 34, for example.
All right, great. Looks like Paul Wolin has a question. Paul, you're unmuted.
Yeah, I have a quick question here. Have you ever thought of maybe doing an overpass versus just a non-overpass probability? Because that's also a problem, is the overpasses ice up much more quickly than the road surfaces do, especially in the shoulder seasons.
Of course, yes. So based on the data set that we had, that we've been using, at least the number of ARWA stations that I've been looking at, we really didn't have probably a representative example, or representative sample of conducting that sort of analysis. I think we only had a couple dozen ARWA sites that explicitly said, oh, we're on a bridge, or oh, this is on an overpass. And so it would have been difficult and probably not really representative analysis.
I'd like to add a thought to that too. One thing that we haven't done is we haven't pinned down the interpretation. So we don't know, for example, if a probability of 30% means there will be accumulations of snow or not. At what point do you need to issue messaging? And so that's something that going forward we're going to have to figure out, is what does a probability of X mean in terms of messaging? Maybe a 20% probability means you start to message on watch out for the bridges and overpasses. And then a probability of 80% means just stay home if you're uncomfortable driving on slippery roads. We just don't know that.
Okay, great. Thanks, Heather and Shawn. I don't see any more questions right now. I really appreciate you taking the time to present this work. We're really excited about it, and I think, like you said, Heather, even without that, the end vision of what you originally were thinking of, I mean, this has a lot of utility for us as far as messaging and that sort of thing. So really appreciate you taking the time to share with us.
Thank you.
Thank you.